Thank you everyone for coming here. Actually, let me just give a very brief introduction. Today's talk is a part of the public activities related to the midterm meeting of an European project. The complete name, let me read the name of the project because it is too long for me to remember. And And the name of the project is PDE-based geometry modeling, image processing, and shape reconstruction, but we usually call it PDE-GIR. So this is the name of our project. And as a part of this public, actually the midterm meeting will take place tomorrow, here also in the University of Seville, at the Institute of Mathematics. But the day before, we organized a couple of activities just to show what are we doing right now in this project. And so the main part of these public activities is this talk about partial differential equation for geometric design. So the speaker of today will be Professor Hassan Gugel. He's a professor from University of Bradford in United Kingdom. And he's also the director of the Center for Visual Computing. So I can say that he's also a good friend of us. So it's also my pleasure to receive him and the other member of this project here in Seville. And it's also my real pleasure to ask Professor Gugel to deliver this very interesting talk to us. Thank you very much.
Thank you, everyone. So thank you, Alfonso, for inviting us for the sunny side of Spain. It's almost too hot, to be honest. I mean, I'm originally from the Maldives, and I come here yesterday, and it looks like, it's probably hotter than Maldives. And Professor Malaysia and we were actually discussing last night over dinner. To me, it's almost too hot to do anything intellectually challenging, to be honest. It's more like you need to go outside and relax a little bit and maybe discuss things rather than doing things intellectually. Anyway, so thanks very much for inviting me. I think it's a pleasure to be here and talking about a topic that's actually very close to my heart. So I've been working on this topic for a number of years, like 15, 20 years. So this is the work that I'm going to be talking about, the work that kind of summarizes quite a lot of what I've been doing over the years, not just myself, a lot of my PhD students, a lot of researchers, a lot of projects. So if I start thanking everyone, I think then the list is very long. So I don't want to thank, but although I'm actually presenting this work, this is not necessarily just my work. So the topic, as you should say, is partial differential equations for geometric design. And I'm sure everybody knows about geometric design, but we are actually going to be looking into a very small segment of geometric design. And to do this, what I like to do is I like to kind of introduce a problem. So we always kind of start from a practical problem and try and see how we can utilize mathematics, partial differential equations, or whatever we want to call it, to solve that problem. So we will start looking into a problem to start with. So let me just, what I'll do is, so we are kind of always fascinated by finding ways to try and implement what we see in real world in the virtual world. Yeah, so we have been fascinated by this idea. So you see me, we see everything that surrounds here. How are we able to actually create exactly this in the virtual world, in the computer, so that we break the uncanny valley? So everybody knows about the uncanny valley. How many of you play games? Yeah, computer games. So you know the character in computer games. When you see it, you know that's not quite real. Yeah, you can see. So humans are very, very good in finding these little faults. So this is what we call the uncanny valley. So in the uncanny valley, you create a geometric design, you create a geometric model. And what you want to do is you want to make it so realistic that kind of, so that you can't see the difference between, so that what we call the Turing test. So you can perform the Turing test and see, you can't tell the difference between the two. So I'm gonna try do a Turing test on you right now. So I've got two videos here. Okay, so one of these videos is actually virtually created. This is a virtual, and the other one is computer generated. So I'm going to perform the Turing test on you now. Let's try and see how many of you get this right. Okay, let's just, so let me start with the first video. Okay, so the first video is this video?
Well, the actor is captured on video, and then the video is analyzed by our computer software, and the actor's performance is used to drive any facial rig.
Right, okay, so you've seen that video. Now, okay, let's try the next video. Okay, so you've seen the two videos now. Now, let's try and ask the audience. So, which one is the actually computer generated one, and which one is the real one? So, hands up those who think that my right, the video on my right, is actually a real video. Okay, and so the other one is virtual. Yeah. Yes or no?
Yes.
Okay. Well, you'll be actually very surprised. These two videos are computer generated. So I lied initially, just to trick you. So you see, we can almost do this sort of work. We can fool people already creating this. But the amount of work that actually went in creating, for example, this video here, which is the one that looks very realistic, is actually quite a lot of work, quite a lot of resources actually gone into creating this. Yeah. So the point I'm trying to make is this is what we want to do. So how do we go about actually creating this sort of things in using mathematical formulations? And as I said, I'm going to be actually addressing not the whole question. Obviously, the whole question is very, very big. So we're going to be addressing a very small part of the question and how we approach the idea. So the idea starts obviously with mathematics. So this is the idea. So you have a character, you have a face in this case that you want to represent in realistically. So you have a textured model, and then underneath you have a mesh. Yeah. So this is the way we create. So you create a mesh, you create a three-dimensional point system, you create a mesh. On top of that, you overlay a texture map. Yeah. So that's exactly how we go about creating characters. But what I'm interested in at the moment is not about the texturing process. What I'm interested in is creating the geometry, the underneath, that 3D mesh there. That's what I'm interested in at the moment. So there are many methods actually. There are a lot of methods at the moment to create this sort of 3D mesh. You might have come across things like NURBS, B-splines, Bezier surfaces, things like that, which are very traditional mathematical concepts. And that has been existed for a number of years, and they are already integrated in pipelines, in geometry pipelines, and so on and so forth. But the way we actually look at this problem is slightly different. So I like to introduce this from a differential geometry point of view, from a differential equation point of view. So to do that, let me go back to kind of a little bit into kind of fluid dynamics first, okay? So you need to bear a little bit with me before I try and introduce this idea and how we go about doing this. So the idea, as I said before, the idea is to create the realistic 3D geometry and be able to also manipulate this. Remember that when you have a character, when you have a geometric character, what you want to do is you want to be able to first create that character, but you also want to bring that to life. So you want to make sure that, for example, it's me, I need to be able to talk, my mouth needs to move properly, my facial expressions need to be there. So there's a lot of things that are happening that will happen underneath through that character. So it's not just about creating a static character, it's also being able to introduce the dynamics into the character, yeah? So to do that, the idea here is, this is the sort of big idea, okay? So the big idea here is, let's start with some very basic things. So you have a heated bar, okay? So this is a metal bar, okay? Now you might be wondering why am I talking about metal bars, but you have to bear with me for a minute. So you have a heated bar. Both sides of this heated bar is insulated. That means there's no heat actually dissipating from those two sides, and you're putting a heat source from on top and a heat source from the bottom, okay? So you have a heated bar. So under steady conditions, when the heated bar reaches steady conditions, you can actually say the internal temperature depends on the temperature that you apply from the top and the bottom, yeah? So imagine you have a temperature H1 at the top and then a temperature H2 at the bottom. So the interior of this, the internal heat, depends on the heat that you apply, yeah? The two heat sources that you apply, okay? There's no heat actually dissipating from the boundaries, but you are applying the heat from the top and the bottom, okay? And then we can say the heat distribution is constant throughout. So you can almost say it's a constant throughout. And the temperature, the overall temperature of the actual metal bar will not exceed H1 plus H2. Yeah, we know that, yeah, because that's how it works. So under steady state conditions, you can actually model this. I mean, this is not a difficult problem. You can actually model this. In fact, this is what Laplace did. You know, so this is essentially if you actually then knew the heat source H1 and then knew the heat source H2, you can work out the temperature at any point in this bar by solving the Laplace equation. Yeah, this is actually, you know, a century-old problem which has been solved by Laplace. You know, so we're not worried about actually the solution, but we are interested in actually taking this idea into geometric modeling problems. So how do we do this? Okay, so that's what we are interested in. So you have H1 and H2, and then you can solve the Laplace equation. So the solution of Laplace equation is the temperature. Now that, remember, the temperature distribution is well kind of, you know, conserved and well distributed. Yeah. So far everything is clear to everyone. Yeah. So how do we turn this into a geometric design problem? Okay. So you have your H1 and H2. Those are boundary conditions. Remember. So those are boundary conditions. And given those boundary conditions, given the Laplace equation, you can solve the Laplace equation and plot the solution of the equation in three-dimensional space. You can actually plot the heat temperature distribution in three-dimensional space. Yeah, easily. And that three-dimensional space, that three-dimensional is a geometry. It's a piece of geometry you can actually visualize. Okay, so this is the basic idea. So as I said, if you imagine this kind of yellow object there, that's the actual solution of the Laplace equation, or a version of Laplace equation, subject to those boundary conditions. So you have boundary conditions at the top, you have boundary conditions at the bottom. Yeah, these boundary conditions are my heat sources. But all I have done is I have just taken a function. A heat source is a function. Yeah. So all I have done is I have taken a function as my boundary condition. I have taken another function at the top as my boundary condition, and then I solve the Laplace equation. But I am actually solving not necessarily the Laplace equation in this case. I'm solving a higher order equation, which is the Biharmonic equation, which is an order higher. So essentially the same characteristics apply. You have the conservation of properties actually do apply in the Biharmonic case as well. Now, I'm not going to be doing the mathematical analysis because it's very cumbersome, it's very involved, but you can take my word here that the actual internal, the shape of the surface here in this case also depends on the boundary conditions. So the boundary conditions, it actually follows. So you will not get, so given these boundary conditions, you will not get any kind of wiggly shapes in between because it actually follows the boundary conditions. So it's a fairly smooth surface. Okay, is everybody clear what I'm doing here? So here all I've done is we've taken the Laplace equation and we've actually increased its order to Biharmonic equation, and then we've taken 4 boundary conditions. So in this case I'm taking a positional boundary condition and also a normal boundary condition. So the normal boundary condition actually lets me tell you how the surface actually moves into the interior from both sides. So given those 4 curves there, you can see those 4 curves, I can solve the Biharmonic equation and get the boundary, get the shape. Yeah. So now the interesting part here is that the actual internal shape of this surface depends on the boundary conditions alone, on those curves. So if I start manipulating those curves, I can start seeing different shapes. So my handles, my manipulation, or my control for that particular object is actually those boundary conditions or those curves. So I can now introduce things like handles. I can introduce, things that can do interactively change the curve, and then solve the biharmonic equation and get the shape. So this is the basic idea that we use. And we have been using this idea for a long, long time. We've been playing with this idea. So what I'm going to do is, I'm going to show you some examples of some of this work, but also I like to do a little bit of mathematical analysis just to show you how we arrive these solutions. Okay? Is everybody clear on this now? So do you have any particular questions? If you have, you can ask me, but we could probably leave the questions for later. But I think people are clear on this. Yeah? Okay. Good. So let's just try and understand the actual process of what's happening here in the biharmonic case. Why I have chosen the actual biharmonic equation rather than the Laplace equation or any other order. Okay. So now you can try and actually look at the biharmonic equation actually and try and see what is it that is actually trying to do here. So let's just take the example here. So you have if you take the Laplace equation is nothing but the average of 4 points around. So if you have these four, if you have this point here, and then if you take the Laplace equation, those four orange squares, so the x is the average of those four orange squares, which is essentially what the Laplace equation is doing. So it's an averaging process. Yeah. Now, if you actually order it higher, so if you actually take the biharmonic equation without the cross derivatives, in this case, let's just remove the cross derivatives for the moment and just take the biharmonic equation, which is the order 4. You are actually averaging across and downward. So it's a vertical and a horizontal, but 2 points each way. Yeah. So you are doing an averaging, which is a cross derivative averaging. Okay. So you are bringing the averaging essentially along the x-axis, along the horizontal axis, and along the y-axis. Yeah. Now, if you keep increasing the order of the PDE, it will do that. But if you introduce the cross derivatives, which is what we are doing here, so you are taking the biharmonic equation. In this case, you can see the averaging actually spreads out. So it's a better averaging process, but it's still averaging. So that's the essential idea behind choosing the biharmonic equation. It gives you better averaging, it gives you better control around the surface, and you can see the averaging process never exceeds any of the points around it. So that's also a good point that we're choosing the biharmonic equation. And that's the kind of idea that we have to actually choose the biharmonic equation rather than the standard fourth order without the cross derivatives. Okay? So so once we understand that, let's move on. So one of the problems that you have is you have the biharmonic equation, and what you want to do is you want to solve this equation. And there are many ways you can solve it. You can use analytic solutions, you can use numerical solutions. There are various numerical type solutions. I'm not going to be talking about those numerical solutions, but what I want to do is I want to talk a little bit about some of the analytical solutions that we are using at the moment. So why do we want analytic solutions? Why not numerical solutions? Well, there are many reasons. Analytic solutions are faster. You can compute it very fast. Yeah. So because they are analytic functions, you can simply compute them. Usually they are exponentials, so cosine and sine functions. So you can actually compute those analytically. Whereas if you've got numerical, then you've got finite element, finite difference, and that sort of thing. So you introduce errors, and also it's computationally cumbersome sometimes. So we tend to actually look into the analytic solution. So here, the biharmonic equation that we use is this equation, and these are the boundary conditions analytically written or mathematically written, and those are kind of my boundary conditions, and the resulting surface is that. Okay. So what we can do is we can go about and write the analytic solution for this equation. So the analytic solution actually looks like this. So you have the surface here, and then you have an A naught, and then you have a cosine function and a sine function. And these A and B n's are some vector valued functions, okay, which we can compute. And these are essentially exponential functions, okay? So all we now do is that, given that equation at the top here, at the surface here, all we now do is we introduce the boundary conditions. using those boundary conditions, we compute these ANIs and A0s and AN1s. Once you compute those, you have an analytic function that can describe your surface. Yeah, so it's fairly straightforward. So far straightforward. But there's a problem here. The problem is, obviously, this analytic function is not appropriate for all types of surfaces. So, for example, imagine you have, so this is based on cosine and sine. So if you do some Fourier analysis on the actual curve, you're not going to be able to get the whole function. So imagine like you have a boundary condition where the boundary condition is a square or rectangle, in which case it is not going to be, the n here, the big N will actually run into infinity before we can get the square out. So it is actually not a practical way to actually do the solutions all the time. So what we do is we actually use a simple trick to play with. So we call it the pseudo-analytic solution. So the way we do it is this. So you start with this surface, and then you assume this is the surface, but also you take that solution, which is n. N is a finite number of Fourier series. So if you imagine you have a very complicated boundary condition, you can take, first of all, n Fourier series, which actually gives you an approximation to the boundary condition. And then what we do is we take that approximation and then the real value at the boundary condition, and we subtract the two, we add that difference to the solution. So so doing that, what happens is the surface the surface actually satisfies exactly the boundary condition, but you have an approximate analytic solution for the biharmonic equation. And if you take n to be something like, let's say, 5 or 6 Fourier modes, usually, and then if you add the difference between it, usually it's fine. So things like this surface here, you can see the boundary conditions that I've used here, quite difficult type, where you have sharp bounds of, in the case of the heart, you can see you have a very sharp boundary corners here, the triangle and so on and so forth. So you can actually do that by adding boundary condition. Are we clear on this? Is everybody sort of, do you understand what I'm doing here? So essentially I take the boundary condition, doesn't matter what it is, I use the Fourier series, I get n terms of the Fourier series, and then obviously if I plot that, it will be a very close approximation. If I take a square, it will be almost like a circle, but it will not fit at the corners. So I take the difference between the Fourier series curve and the original curve, and then I add that difference to the solution. So it actually satisfies the boundaries exactly. So this idea is again not very old, not very new. It's actually been existing since 1996 by Blair and Wilson, and other people have actually worked on this for a long time. So we've kind of taken that idea, we've utilized it. Okay, so that's essentially how we do the spectral analysis. So the work actually started as a PhD student. So this is kind of my first paper on this, which is actually to do with interactive design. So the idea was you take these biharmonic equations and start manipulating these shapes using the boundary curves. So this is published in SEM Transactions on Graphics, which is the only paper I have in SIGGRAPH, and probably the most cited paper for me, I think. But that paper gives you an overview of all I have just talked about, essentially, so far. So you can probably look at that paper. So here are some examples of the sort of PDE shapes that you can create. So all of these are created using the biharmonic equation. All you do is you identify the boundary conditions, the characteristic curves, and then based on that, you solve the biharmonic equation. In this case, in the case of, for example, the dolphin or the dinosaur, you see there's a number of patches actually connected together to form the actual the actual shape. So you actually need to start looking at the derivative continuity and things like that. So sometimes we actually go a little bit higher order sometimes if you need continuity between the patches. So sometimes you can go to a higher order PDE also. So the interesting thing here is once you have this sort of idea, you can start then manipulating these curves, you can start manipulating these shapes very quickly. And you can start introducing time parameters into the boundary conditions as well. So once you start introducing the time parameter into the boundary conditions, you can start actually animating these things. and you can start adding functionality into the actual geometry. And we have done quite a lot of experiments, and we have done quite a number of examples of this sort of work. Okay, right. So so one parameter that we actually use quite a lot is what we call the spine of it. So let's just go back to the actual solution here. So remember, this is my solution, my analytic solution, S of u v a naught, and then you have the sigma a and cosine, and then b and the sine of. Yeah, so this is my analytic solution. Now the analytic solution breaks down into this form. So you have an a naught, which is a polynomial function, and then you have a n of u and b n of u, which are the exponential functions. But if you look at that a naught u, which is the polynomial function, if I plot that polynomial, the polynomial is actually the spine of that particular shape. Yeah, so you have the actual shape, and then if I plotted the actual polynomial function, it's actually the spine of that object. Now I can start using that spine to actually start manipulating things. And this is exactly what we have done in this case, in the dinosaur case. So we've taken the spine and we started manipulating the spine. So how do you start manipulating the spine? Essentially, you just change the variables in the constants in a naught, a naught 1, a naught 2, a naught 3. So you just change the constants. You can change the shape of the spine, or you can just use some sort of interactive tool to start manipulating and changing the functions in the polynomial. Okay, so you can do this, and that becomes a very powerful handle to start manipulating these shapes as well. So we've done quite a lot of work in this. One of the things that people actually use is the traditional techniques, things like Bezier surfaces, other sort of polynomial functions. So we wanted to actually show that we could constrain such objects also using the biharmonic function. So here, this example is, you have a standard Bezier surface. Everybody, all familiar with Bezier surfaces, yeah? So you have a set of control points, and then you have a network of polynomials, yeah? And that those polynomials are constrained so that you have some nice functionality. But the interesting thing here is that you have a lot of control points, and then when you start pulling all these control points, you lose control quite quickly because it's cumbersome. So what we've done is we've actually said, okay, sometimes you need surfaces which are nice, which are smooth, which are functionally good. So you can actually use the biharmonic idea, and you can constrain the Bezier surface to a biharmonic function. So this idea here is that you have a Bezier surface, but what you want to do is you want to constrain it into a biharmonic function. So this is what we call the biharmonic Bezier surface. So it's a Bezier surface, at the same time it's biharmonic, so it satisfies the biharmonic equation. Yeah, so we call it bi. So this is sometimes useful when you're designing things for functionality purposes and things like that. So what I'll do is I'll actually run through some of the applications of the examples. There's quite a lot of things that we have done, but I've just picked a few examples just to show you the application side of these things. So this is an example where we're looking at face recognition. So the idea of face recognition is, this is not standard face recognition. This is actually 3D face recognition. So 2D face recognition is very common, but we were actually at some point, we were interested in 3D face recognition. So when you have a 3D face recognition, the first thing you have is you have a 3D scanner, you capture somebody's face. You get a point cloud, yeah? Now this is a very dense point cloud, yeah? Usually you are looking at, the simplest of, if you constrain all the features, if you want to keep all the features up to a point of an identical twin, you need about a megabyte of data for each individual. Now, you might think a megabyte is actually small, but imagine the whole population of Spain, a megabyte each. Now, that's a huge data set. Now, forget about searching to start with, but that data set is actually very huge. So one way you could do is you can actually try and reduce that data set. So the way we do is we actually use the PDE technology to reduce the data size. So how do we do it? We actually take these section curves, and then we identify key points. So what are the key points on a human face? So if you look at the face, if you divide the face into two halves, the symmetry profile, for example, the symmetry profile is unique if you take identical twins, and then look at the symmetry profile, that's actually unique. So one way you can do is you can preserve the symmetry profile. in 3D. In 3D, it's a curve. So you can try and identify these features on the face and make sure that those features are preserved. At the same time, there's 3D geometry in it. So the way we do it is we actually take an original scan. So this is a scan. This is actually my face scan. And the curves, there are the curves that are extracted automatically. And we can actually save those curves. Simply saving those curves reduces from 1 megabyte to 30 kilobyte of data. Now, the interesting thing is that 30 kilobytes, I can actually then use the PDE to recreate my face using that 30 kilobytes because I have got the key information of the face. So all I need is use those curves as boundary conditions, solve my PDE, my Biharmonic equation, and then I get the face. So it's a way of actually compressing data you could imagine. In fact, we have played with this idea quite a lot. I'll talk a little bit more about it later on, but we have actually played this idea quite a bit, and there are several patents on this as well that we have applied. So the idea is taking an existing geometry and find out the character lines of that object, and then save those character lines, use the PDE, the analytic version or whatever it is, and then solve the PDE later on to recreate the geometry. Okay, so that's an example. Here's an example. So one of the things that you could do is once you have those the parameterized geometry, we call it, the parameterized in the sense that you can introduce parameters on the boundary curves and the spine and so on and so forth, and change these parameters and go from one shape to the other. So this example here, we were looking into pharmaceutical tablet design. So the idea is the crushing ability of pharmaceutical tablets apparently is an interesting problem in pharmaceutical industry. So what we were interested in is trying to find the best shape of the tablet. So you have different shapes of the tablets, but sometimes the actual shape, defines quite a lot of things like the crushing ability and other things. So the idea here is how do you come up with the best uniform or the optimal shape of the pharmaceutical tablet? So what you can do is you can actually design a tablet using this idea. So you have the boundary conditions, you can create it. And then you can introduce parameters. So you can introduce functionality on these boundary conditions. And you can run an optimization problem. So the idea is you have a function that you want to minimize. Let's say you want to minimize the volume, or you want to minimize some other function. But then you can start changing the parameters, the boundary conditions, and then you can start running the optimization until you get an optimal function. So that's the essential idea. So you can get different shapes of the tablets based on the original kind of parameters that you take and the obviously the optimization problem that you're setting up. So that's one example. And here's also an interesting project where we were looking at thin-walled structures. Now, thin-walled structures are a lot. You have plastic bottles, you have containers, and so on and so forth. There are many, many varieties of these objects. And again, the idea is to try and reduce the amount of plastic that goes into it, but at the same time, you want to keep the functionality intact. So imagine like even if you can knock out a few grams from your standard margarine tub or something, you can reduce you can reduce quite a lot of expenses by just knocking out a few grams. So the idea is you set up the actual optimization problem. You set up an original shape, and then you set up the boundary curve structure, and then you introduce parameters to these boundary curves, and then you run an optimization problem. In this case, maybe the crushing ability, maybe the volume, or whatever it is, but you have a function. And what you want to do is you want to run standard optimization and create the optimal design. So, for example, here, starting with this shape, here's an optimal shape that we came up with the same volume, but less plastic, So that's how you could actually do this. So that's another idea that you could use for this sort of work. Okay. Now, so moving on, here we were looking into things like modeling and animation. So as I said, we could start introducing time parameters into these boundary conditions, and then those time parameters actually then allows us to start giving life to these objects. So let's just give you an example of a video. So you'll see some fish on this video. No, you don't. video is not working. Okay, I think that video is not working, but you can see the animation on the faces. So you can see. So this is called what we call motion retargeting. So you have somebody's kind of motion captured before, and then what you want to do is you want to retarget this motion to another face. So let's just say you have Robert De Niro's face and my facial expressions. I want to put those expressions into Robert De Niro's face. Yeah, always. Is you actually create a parameterized head model using the PD formulation, use the curve structure, and then get the animation and then target it. And of course, people like Professor Yu and other people have done quite a lot of work on this, on horse motion and other things. Again, so this is this idea has been taken forward into animation and other character modeling as well. So that's that. So this is I think this is my final slide. I think, yeah. So this is tangentics. So I want to tell you a story about this. So some years back, when we were working on this, some venture capitalists came to us and they said, "We are interested in your technology." Yeah. And then I said, "What is it? Why are you interested in this?" They said, "We are interested in taking this technology into game." I said, "How?" They said, "Don't worry, so give us your patent." So basically, they formed a company with myself at the University of Bradford called Tangentics. You can look it up, actually. So what Tangentics does is this. So what they've done is they've taken our idea of compression technology. So it's compressing. So you take a computer game, you have characters in the computer game. So you have the actual characters, you have the texture and things like that as well on top of the character. So what they're doing is they're taking existing computer games, the actual data in there, which is quite huge. If you look at a big game that takes like gigabytes of data, and it takes time to actually download. So the way they are doing now is they're taking this idea and taking the characters and then using the PD version of those characters, and that actually brings it down quite a bit. The size. So imagine the example I gave you before, where you have the face from 1 megabyte to 30 kilobytes. So in a similar way, what they've done is they've taken this idea and they've created an engine where you can actually compress the geometry. So let me just show you this example. This is a very, very early example of that. In fact, this is a first demo. So you see a character here. Again, I think this video is not working. But anyway, doesn't matter. So the point is, you have a character, and this character is actually defined analytically. Essentially, as the geometry is. So, for example, you have a character. If it's very far, you don't need to render that character very in detail. If it's coming close by, you need to render very in high detail, and you can do this dynamically with the PD, because all you have is you have an analytic function. So that means you can compute what resolution you want in real time. So you can keep computing that. So that's the idea behind it. And what they've done is they've taken existing games and all they're doing is they create the PD version of those games, the geometry and the texture, and then put it online. And then what you can do is you can start streaming these onto your device. So you don't actually need to even download your game. You can start streaming into the device and you can play it. Because it's so fast, you can interact with the characters in real time with these things. Whereas if you go to a traditional version, you have like gigabytes of data to download, and that takes time. And then when you do something, you need to send back an instruction to the server and then bring it back. So it becomes a little bit cumbersome. So the way they have done is they have actually taken the PD idea and essentially used it for geometry compression. In fact, they have actually used it for texture compression as well. So they are now doing texture compression as well using this technology. So if you happen to go to internet and look it up, gamesessions.com, this is actually now. They have invested something like 6 to 10 million pounds on this entity, and I think they're talking to big companies to try and see whether they can work with Amazon and Microsoft. So it's a big thing. So it's something I'm a little bit proud of in a sense. You've done all this work and you see the real value of it in especially in gaming industry. So just to conclude, the PD idea is interesting. I've been working on it for a long time. Obviously, I will push it forward because it's something that I have been interested. But I think a lot of people have found this idea very, very interesting. And there's a lot of work that has actually happened through this idea. A lot of interesting work, lots of projects and of course the PDGIR project is part of it that we want to push forward. So I think that's about it, and I'm happy to take questions. Thanks very much for listening to me. Thank you. Yeah, Professor Melis.
You prefer to use biharmonic equations.
Yes,
right?
yes.
Can you explain why you use the biharmonic instead of Laplacian?
Yeah, so
equation?
Sure, yeah, exactly. This is a very good question. So why do you use the biharmonic, not the Laplace? Okay. So if you imagine Laplace equation, you remember that my example of the heat. So you have a curve at the top and you have a curve at the bottom, and you solve the Laplace equation. Okay. So you will get a shape internally, yeah? But I can't control anything internally with the Laplace. All I can do is just change the boundary condition, change that shape, yeah? Whereas if I can then if I can add another boundary condition, like a normal, yeah, which lets me use the biharmonic, then I can also start controlling the internal shape with those. So I can have the curve, I can also introduce...
So you have more freedom.
Yeah, exactly. Yeah, you have more freedom, yeah. So you can even go higher up. You can do sixth order, but the problem with the sixth order, and then if you go higher order, you lose internal control because there's a Minimax theorem. I don't know if you know about the Minimax theorem, which says that Minimax theorem works for Laplace equation. But if you go higher up, biharmonic equation, Minimax theorem sort of works. But if you go higher up, like the sixth order, I think Minimax theorem fails. Although it still will work for nice, smooth boundary conditions, but I think it will fail. So this is why we tend to go for the biharmonic. Yeah?
Next question.
Yeah, okay. Yeah.
So if you have a shape,
Yeah.
and on the shape you have some edges.
Yeah.
And how in this technology you can control these edges?
So do you want to control the edges or do you want to preserve them?
For example, preserve. You can have very complicated surface with many edges.
Yeah, sure. Yeah.
And you would like to preserve.
Yeah. So one way you could do it, the way we do it is we actually take the biharmonic version and then we take the difference between the original and then add that to that, because that's something that you want to preserve. So those are that geometry is often not very huge. So these are just point sets essentially. So what you can do is you can actually add that to the biharmonic equation, the solution, and you preserve it. You can still then control it and then keep adding, whenever you make a change, you can keep adding that. That's one way to do it. The other way to do it is you introduce those edges into the boundary condition itself and use the pseudo-analytic solution. Yeah. Yeah, Nico.
Yeah, I found that you are going to use the deep learning to solve the PDE.
Yeah.
My question is why, what's the advantage you introduce deep learning into solve PDE?
Yeah.
And what will your research cover?
Yeah. So we have been recently playing about this. I mean, I have actually introduced the analytic solution version, and it works very fast. So the idea here is that obviously the analytic solution doesn't work for all types. You have to use the pseudo-analytic solution. You have to get the boundary conditions and then play with it a little bit to be able to kind of get the proper solution. So one idea that we've been playing with is what we call machine learning. So the idea is you show lots of solutions, examples to that, and then you try and work out a function that can solve the biharmonic or whatever PDE very fast. So the idea is to train a model, and then once you train the model, you can then show at the boundary conditions it should be able to evaluate tell me the solution very quickly. So it's making it fast, but this is still very initial stages of this idea. I don't know how far we can push this idea. It seems to me when we looked at the Laplace equation, for example, it seems to work with this. So we have some interesting results at this point. So the Poisson's equation works, but when we push it to the biharmonic and higher order, I don't know what's going to happen. Yeah. And also deep learning is a very sexy topic these days. So it's good for funding. You know, if you put deep learning, if you put machine learning, you know, your proposal wins money. So it's good also to inject those ideas a little bit. But I mean, apart from that, it's a very, very interesting idea, you know, so why not?
Is there any other question?
The last question.
Yeah.
About, again, this shapes traditional approach. You know, you construct a solution.
Yeah.
For with this spectral approach.
Yes, yes.
And you have some parameterization.
Yeah.
And so I doubt that it will be quite complicated again if you have, for example, again, a complicated surface topologically involved, you know. So how to
so just give me an example.
To design, you know.
The face is a very complicated geometry, isn't it? So we can do the face example. I mean,
but it can be more complicated. You know, if, for example, some systems of tubes, you know, like
are these theoretical surfaces?
Yeah, and
yeah, if they're theoretical surfaces, yes. For example, I can't create a sphere using this. I can't create a sphere, so you know it's impossible because. You know, but do I need to create a sphere using this? I have an analytic, you know, solution already, an analytic representation of the sphere. So why would I want to use PDEs to create the sphere? This question comes up because yes, you're right. So it's not kind of universal to be able to create kind of any theoretical. For example, I can't create a Klein's bottle using this.
Mm-hmm.
There are many things that I cannot do it. But then again, do I want to do this? Because you know, there is already an analytic solution to that, so you might as well use that.
So you want to conclude that in practical situations, you manage to
yes, exactly, yeah. So the whole idea is applied, you know, to try and solve practical problems, yes. And then, of course, the question of the theoretical question does exist. Can we actually universally represent any object using the solution of a PDE? I'm not sure. I don't know. I mean, it's a very interesting question to kind of explore, but I haven't got time to do that yet. You know, so okay. Thanks very much, everyone. Thank you.
Thank you very much.
Yes.
Thank you for coming, especially not only for